keep muting. I don't know. I apologize. I don't know why my thing keeps muting automatically. Thank you for letting me know. It's very frustrating, but it's Zoom for you. So we're going to do AC machines. We're going to look at how we take advantage of alternating current to develop. And here's the key thing. It's a varying magnetic field. Now, the magnitude is not going to vary. The magnetic field, we would like it to be as constant as possible, because the only way to really get constant torque out of a machine is to make sure you have a constant magnetic field. Because remember, magnetic fields, they either repel or attract. So if you have a constant magnetic field and the repelling or attraction is going to be constant. But if the magnitude of that magnetic field is increasing or decreasing, you're going to have more or less force, which means you're going to get more or less vibration. That's the thing about vibration. If things are accelerating or decelerating over time, that equates to vibration. And so as much as you can, you want to limit the vibration. So when I'm talking about the varying magnetic field, I'm talking about its rotation. So we're going to actually have a net magnetic field in our machines, and we're going to see how that net magnetic field rotates inside that machine at a really nice constant rate, and it actually doesn't vary its magnitude. AC machines can do both. That's why we call them a machine. They can do power consumption or power conversion. Either one, they can go either way. I guess they're converting power in both cases, but when I look at it from a motor's perspective, it's converting electric power to mechanical power. If it's a generator's perspective, it's converting mechanical power to electrical power, okay? So we don't really consume energy in a motor, we transfer it over to the mechanical load. And they are incredibly important in industrial facilities. You can go and look for Baldor, Reliance, GE, Hitachi, they're big motor manufacturers, and you see them all over the place. Okay, tons and tons and tons of three-phase motors really make our life easy. Okay, so we just need to go ahead and if you remember from chapter 1, generator action, we need to get that perpendicular plane or orthogonal plane to the field and the current direction, and our motion is going to be indicated in that way. That is less interesting to us than actually looking at voltages, how we induce a voltage in the machine, and how we're going to introduce torque in the machine. Remember, the motor is going to convert electrical power to mechanical power, so it should generate a torque. Whereas the generator is going to convert mechanical power to electrical power. So you need to be able to generate torque, or you need to be able to generate a voltage so that you can drive a current to the load. And what we see here is if you make an actual physical machine, you can get really nice looking voltages, like in the case of a generator, or nice looking torque in the case of a motor. And the idea is that we want this to be as smooth as possible, because that allows us to have smooth operation, and it also allows us to have balanced power systems. Remember, our voltage should look like a perfect sine wave as much as possible. And it should have the phase relationships that we need for 120 degrees. If this does not look like a perfect sine wave, then what we have is harmonics. And depending on who you are, most of the time harmonics are bad things for us. We actually want to avoid harmonics at all costs in most cases. Sometimes we can't, like if we're listening to music, we have to deal with some kind of harmonic distortion, but as much as possible, we would like to limit that. So if we have a well-built machine, we can get pretty sinusoidal outputs. All right. So here's our basic three-phase machine. Now, here's the key thing. When you have a motor or a generator, you have two sets of windings. You have a stationary set of windings and a rotary set of windings. Okay? You always have two sets of windings. What we see here is the stationary set of windings. These windings are on an object that is not moving. It is just sitting there, ready to accept current. So what that means is I can run my phase currents into those windings, and those windings are arbitrary. Those are literally just 3 copper windings, exactly the same on the machine, and they're just spaced physically 120 degrees. All right. So we have 3 sets of windings. It only becomes the A winding when we connect phase A from our power supply. All right. So it's not actually the A winding, it's winding 1, winding 2, winding 3. Do you remember on the test when I gave you that transformer equivalent, you had to go ahead and actually figure out, take the test data and convert that test data to equivalent circuit parameters? Do you remember how the terminals on the transformer were written? H or X1, H or X2, H or X3. The reason why they don't call it A, B, and C is because you can connect it any way you want. So we're just coming up with a convention to name it. It's the same thing on these machines. What's different here, though, is we have A, B, C, and on the transformers, we had 3 windings on the primary winding. This one, we only have 1 set of windings because these motors or generators don't step voltage up or down, but we have the windings. And you'll notice the C and the C prime winding, that's the other end of the winding that comes out of the machine. So that's the return leg, if you will, for the current. So what we see is current goes into the C and comes out of the C prime. Okay, we'll look at how we can show that a little bit clearer. But that's essentially what it is. So when you buy an AC machine, you can actually go into the motor junction box and you can see that there are 6 leads that come out of that. And those are all because they're independent from each other. It's only when they're connected externally, meaning at the motor junction box or even further out, that you actually create a 3-phase machine. I could get a single-phase generator or motor by just connecting phase A. It wouldn't run very well, but I could get a motor or a generator out of that. Yes, sir. Yep. Stators, the stationary part. I was doing it generically, call it a stator or stationary winding. But yeah, would be the stator. Yep. So again, phase rotation or physical rotation, to go from here to here is 120 degrees. To go from B to C is 120. And to go from C to A is 120 degrees. One thing I will say about this figure is that it's a very simplistic representation of a machine because windings are distributed around the entire perimeter of the motor or the machine because you don't want to waste space. What I'm showing here is just sort of the center location of the winding, all right? Just to make the math and the work a little bit easier. But if you were to look at a physical motor in the real world, and we'll see those at some point when we get to lab, you actually see their windings completely wrapping the perimeter of the motor. All right, so now we got to hit it with some current. Let's energize. We've got 3-phase current source because we have a 3-phase motor or the ability to have a 3-phase motor. So let's feed it with currents, but instead of doing steady state AC currents, we're going to mix that up a little bit because we're actually trying to figure out what the rotation is inside this machine. So the only way that we're going to get rotation is if our currents are going to rotate, which means we are rotating through the sine wave, right? A sine wave goes up and down. We would consider that rotation from a perspective. So I'm showing you the actual time domain currents with the proper phase shifts. By the way, can you tell me what type of phasing this is? Is this ABC or ACB phase rotation? ACB? Everybody agree with Barzilay? I only got 2 yeses. Anybody else? 3, 4, 5. You can also say, I don't know. You don't know? Change your vote. Doesn't matter. Well, on this is the current. So the motor is completely separate. The machine is completely separate. I'm just talking about the incoming currents to the where I'm going to connect to the motor. Is this ABC or ACB? Let's draw a picture. Here's A. Here's B. Here's C. Anybody want to change their vote? Did you vote before? But you're voting. You abstained. Yeah, because I see A first, then B, then C. So this is A, B, C rotation. Whenever you're stuck, draw a phasor diagram. That hopefully reveals it. So I've got 3 currents. A, B, C, they're balanced, which is a good thing. I want them to be balanced because I want balanced output torques. So we're going to see, and here's the key thing. Here's our premise. Your magnetic field that results from the three-phase voltage or current that is supplied to the machine will always be 1.5 times the maximum magnetic field you get from one phase. So if you're in this current over here, and you're getting the maximum magnetic field contribution in the machine, the sum of these other two magnetic fields that you get from here is always going to be 1.5 times that individual value. Okay? It never varies. And we want this because we want that constant torque. We do not want a varying magnetic field. All right. So one of the other things is we talked about that 120 degrees displacement. It actually, and we'll see by the end of this chapter, it actually doesn't need to be 120 degrees. We'll see how we can vary that a little bit. But the key thing is we want to create a magnetic field that this BA rotates all the way around 360 degrees. So when that rotates all the way around, something that's chasing it or being repelled by it is also going to rotate at about that same speed. So our speed of operation, and in this case, we're going to keep it really simple. We're going to call it synchronous speed, but we'll actually see how it becomes mechanical speed. We can directly determine what that synchronous speed is by knowing what our electrical frequency is, multiplying it by 120, and then dividing by the number of poles in our machine. This is a two-pole machine that we have on this figure. Why is it a two-pole machine? Can you tell? Yeah, you can't have a north without a south, right? So you have to have two poles. You always have to have an even number of poles in a magnetic system. I mean, they talked about a unipole where they only have one north, but I don't think anybody's ever proven that. But the idea is that you always need a north and a south. So N is always, our P is always going to be an even number. So your speed of operation, the lowest number of poles you can have is 2, right? If you have less than 2, then you don't have a magnetic field. So if we live in 60 hertz land, this is going to be 7,200 divided by the number of poles. So the speed of operation can be 3,600. We can have 4 poles, 1,800. 6 poles, 1,200. 8 poles, and on and on and on and on and on. Yes, sir.
How do you want the speed of operation?
Excellent question. Why would I want the speed of operation to be lower? What's that? Higher torque is one of the big ones. But let's take the example of a hydroelectric dam. How does a hydroelectric dam work? You got water up here, and you've got an outlet that's over here. So the inlet and the outlet, there's a height difference. And then that water is directed through basically a propeller or an impeller, and that connects to a generator. How fast can that water realistically move through that? Not that fast. So in that case, you would have something that spins at a low speed. How about anybody's car engine here? When you jump in your car and you're going 80 miles an hour down the road, what does your tachometer say? 3,000 RPM? 4,000 RPM? So it depends on what you're trying to drive or what is driving you. There are some compressors and all that stuff, they want to run around 1,800 RPM. But then they have hydroelectric facilities that like to run at 40 RPM or around 40 RPM. So it's all dependent on what it's driving or what it's being driven and what is the optimum for that. Yes, sir.
Would it be cheaper to have the generator?
So the question is it cheaper to be less poles? To a certain extent, yes. Once you start getting below or getting above 6 poles, it actually gets more expensive. But anywhere from 6 to 2, there's not a huge price difference. There's a little bit, but not a huge price difference. So really, it just is like here, what the mechanical system is, that's what the majority of the cost is gonna be. So I'll just make my motor or my machine have the right number of poles to match. Most machines, at least motors, tend to be 4-pole machines, because that's like where it's a good number from a mechanical perspective. You can make pumps and pumps and compressors and that type of stuff work pretty well, running around 1800 RPM. Generators tends to be 1800 or 3600 RPM, unless you have a reciprocating engines. Reciprocating engines, most of those are 18 or 3600 RPM, except for quality built ones. So like if you're a diesel generator and you're on the islands of Samoa, where you don't have a lot of capacity, you want these engines to run for very long periods of time. And as he pointed out, with big BP engines, you get a lot of torque. So you run them at slow speed, they just have to be built with more material. High-speed engines have way less metals, so they're not designed to last nearly as long as a slow speed. So you can go to Caterpillar or you can go to Cummins and look at their websites, and you can actually see and compare high-speed versus low-speed diesel, compare a 2-megawatt machine and see what the costs are. Low-speed diesels usually are much more expensive. Yes, sir.
Does the speed increase when you increase the number of poles, increase the time?
Well, this is a 2-pole machine, 4-pole, 6, 8. You tell me. Does the speed increase or does it decrease with the number of poles? As you increase the number of poles, you decrease the speed. And it has to do with, remember, in this winding here, I want the magnetic field from the combination of these, let's just make it BA. I want that to be a peak at some point. Well, if I can split the magnetic field in half, I have a BA over here, and then I have another BA over here. Now I only have to rotate that at 180 degrees. So it doesn't have to physically spin as fast to have another north and south at that specific location. So by increasing the number of poles, you basically are cutting the machine in half, and from a magnetics perspective. Okay, so here are our magnetic fields as a result of ACB rotation. So you can see our when we just call them cosine just to make it easier. And you can see when I'm running along with this current here, this is my current for phase A, you can see that the way this is connected, when this is my 0, I have my red vector at its maximum. Then when I take my yellow and blue, which are both down here, those are negative. Well, it's interesting. How do I end up with a magnetic field going in this direction and a magnetic field going in this direction? This is when you get to use your hand. And because it's very difficult to use your FBI thing, you can actually take your fingers and point into the direction of current. So if I have positive current going into A, my fingers align in the direction of A. Then I wrap around where the return winding comes. So it comes like this. It doesn't go down like this. That goes into no man's land. It goes this way. And the corresponding magnetic field that I get is in the direction of my thumb. So that's why I have magnetic field A in this direction. Now, remember what I said, A is where the current's going in. So normally it's better. Anybody here in the bow and arrows? When you're shooting an arrow, if you're really fast eyes, what do you see going away from you? The quiver, right? The quills. That's what they call it, flushing. Fletching. If somebody's aiming at you, what do you see? An early death? You see a point because that's where the tip of the arrow is coming at, right? So you can see here, I see the felch, is that what you said? Fletch, sorry. I see the fletch here, and over here I see the dot coming at me. And interestingly enough, I'm at my peak current. So the maximum amount of current going in, look at the size of X and the dot relative to the size of the dot and X for B. Much, much bigger, right? See, physically, you can see that represented here. So that's why, that's its maximum value. Now take a look at B and run my current into the B winding and wrap around. Hey, wait a minute, Paul, you made a mistake. Isn't my thumb pointing down? But I have it pointing up over here. Why is that? What's the current going into B? Tell me the number. Look at the plot, the graph. What is it? Negative 0.5. So it doesn't go down here. It goes in the other way, doesn't it? It goes into the B prime winding. So alternating current, it can go this way or it can go this way. It just depends on where you are in the sine wave. So now you have to look, oh, I'm getting a negative current. So the current actually goes into the B prime winding, not the B. Then when I wrap my fingers, my thumb points up a shown. And if you look at that net magnetic field, it's about half, not net magnetic field, the magnetic field because of the current B, it's about half the magnitude is for the current from A. Yes, sir.
Can you do the right thing, the right hand again?
Well, I'm multiplying a little bit. I'm taking my right hand and my fingers go in the direction of current. They follow the direction of current. Then they wrap around in the direction of the winding. So the winding's coming around and back on the back side of the motor, and it's coming right at me. And my thumb points this way. Why am I doing that? Because this gives me the orthogonal vector, doesn't it? If I look at my thumb is perpendicular to my fingers rotating. So I'm just trying to find that orthogonal vector.
And then this is the diagonal of the pulse.
Say that again.
What's
The thumb points in the direction of the magnetic field resulting. We don't have any force yet because we need two forces. I mean, two magnetic fields to get a force. We're just getting magnetic field.
so which one were you, which graph were you doing?
The red one is A. The blue one is B. And the C one, because it's negative, right? It's going in the C prime winding, is the yellow one. All right, let's go to the next slide. Let's see if this helps. So that one was over here. We have A, right at 0 degrees. That's our magnetic field. Then we go to 90 degrees ahead. Now, how much current is going into winding A? None. So look, those are empty. There's no dots and X's, correct? Look at B and C. Now those are both, that one's positive, that one's negative. So my current now, C, is going in the positive direction. My thumb points up in C, and it's 0.866 of its peak value. Not at its peak value, but it's closer than it was before. And then B is a negative number, so it goes into B prime. So I get that over here. And when I add those up vectorially, I get this, right? The imaginary parts cancel each other out. I'm only left with that real part, and I go from there. Same thing here, where I have the Y parts cancel each other out, and then I'm only left with the X part, which adds to this vector. That's why I have that little bit over here. Let me show this real quick. Maybe this will help. Follow it along. Showing you the pictures, it shows you the X's and the dots, and then the magnetic fields, and you can see it rotating all the way along from 0 degrees to 360 degrees. See how all the vectors change color? And then they get filled with, and then the windings get filled in the right directions. You'll also notice it shows you the net magnetic field, which is that black line. Does its magnitude ever change? Not at all. But it rotates along. And I'm doing it in 15-degree steps, but it rotates precisely as it's supposed to. It also shows you, so that's the net magnetic field. We drew it as a vector, but the actual flux flow in the machine is the two lung-shaped or kidney-shaped objects there. You can actually see that the the magnetic field travels in through the iron and tries to stay inside. So this one is the stator. This part here is the stator. This is the rotor. So you can actually see I've added in that piece of mechanical, that piece of metal. And then you also notice that there's an air gap. You see the air gap in there between the two because they physically can't touch each other. But we're showing the magnetic field tends to stay within inside the magnetic material. Question on that?
Do the X's represent in or out?
You tell me. You're the Fletch guy, right? When you're looking at the back of the Fletch, it's in. And the point is the arrows coming at you. So the X is into the page or into the screen, and the dot is out of the page. But it also shows you the relative magnitude of the X's and the dots, as well as the direction. The X's and the dot will flip around. You will notice that they always go to 0 before the direction flips around. And that's what we need to do because inductors, your current can't instantaneously change. You can't go in one direction and instantaneously go to the other one. You have to work through that AC. So that's another reason why AC is so important, because inductors don't fight us so much if we follow that convention. Okay. So let's do some vector math. And the vector math is, all I know is that if I have a magnetic field going into the A winding, the current flows there, I'm going to get a current, positive current in that direction. So this has to have an angle of 0. It always is going to have an angle of 0. If I run positive current into that winding, it's always at 0 degrees. If I run positive current in the B winding, which one is B? Down here. Then what I see is if I run positive current in the B, it's always going to produce a magnetic field that is down at this angle, 240 degrees. And lastly, for my C winding, if I run positive current into the C winding, my thumb is going to point up. I get 120 degrees. Okay.
Where do you have the current?
The current, where is the current? There's no current in here because this is magnetic field. But the current determines what the magnetic field is. And the generic equation for that is you run phase A current through that winding, you're going to get some magnetic field. And its peak value is going to be when the current through there is its peak value. So I'm going to go ahead and say, I get some value B. I don't know what it is, and I don't really care. I just know that it's going to follow the sine wave. Because if positive current goes in, the sine of 30 degrees is a positive number, and the magnitude of the current is 1/2. So I get 1/2 that peak magnetic field. If I get to 90 degrees, I get the positive peak. If I go to 210 degrees, now the current is negative, right? It's down the sine wave. So now I get negative current. Well, the sine of minus 210 degrees is what? I believe it's minus 1/2, right? So now I've got negative current and I get the correct magnitude. So I'm using the current, what the actual current is supplied for, to actually help me determine what the actual BA is going to be. And it varies with respect to time. So BM sine of omega t, BM sine of omega t minus 20, BM sine of omega t minus 240. I got those from there, from the current. If I run IA, which has this form in the time domain, and I run it into some magnetic material, it's going to produce a magnetic material, a magnetic field, or flux density, right? A B, that is determined by the material of the machine, the air gap. There's a whole bunch of different things. We don't need to worry about all that detail. We're just worried about what does that magnetic field look like. That's what I have here. So this is because of the physical layout. And this is because of the current. Those magnetic fields are determined by those. Confused looks?
I think I'm trying to understand the picture, like I'll try just, I'm, able to visualize it. So I really, if I can visualize how you seeing it, I'm seeing different things than what you are seeing.
It's hard, yes. That's why I have this figure in here, which hopefully if you walk it through and you slow down the video, like if you pause it, and unfortunately, I don't have a way of pausing it. Sort of, yes, yep.
Can you go back to the previous picture? No, no, no. Okay, it's fine. So the line, the arrow, the line from B, BA, BE,
BA and BE?
those are, yeah, small BA.
Oh, the magnetic fields that
Yeah.
result from the current flows, yeah.
On the previous one, it was current. On the previous one, on
This one's current.
go back again a little bit. Oh, so all those,
It's always been magnetic field.
and then the dot inside of the current.
That's the current, yes. Because how am I gonna get current flow in here? There's no winding connection, there's no electricity. That'd have to jump through the air gap, right? And this is iron, this is not a great conductor for electricity. So this can't be current. It has to be the magnetic field. And as we mentioned in chapter 1, magnetic field can travel through the air pretty well. That's why we have magnetic fields here. We don't have current. The current only lives in the windings.
So which finger is for the current again?
Not the finger, the fingers. I need all my fingers because I'm looking for that orthogonal vector.
So let's put the red one, for instance. We on top there, it goes out, so it goes out.
Nope, it's the bottom. Remember, it's the arrows. When you're looking at an arrow, you're looking at the X that's going away from you, right? And then if I aim an arrow at you, it's the point that's coming towards you. So current is going in here and out here.
The top one goes out.
Yes, so that's why your fingers go like this and this. And you're up that way.
Yeah, but I must first decide to get your view. Because when I'm looking at
Yes.
that picture, it's pointing this side, it's pointing this side.
Yeah, you gotta imagine it from my perspective, but that's why if you show the X and the Y, all you really need to do is connect it with a vector here. I mean, a plane. And then your thumb just has to point in the direction. So you get the perpendicular plane, and then you need that that thumb to point in the right direction.
When I'm doing, pointing this direction.
Yeah, you're going backwards to me. You're opposite. Steven, and then
Oh, any question about that? Would there be a rehab?
no. Hold on that question because I want to make sure.
What a phase shift of 180 direction.
Phase shift of 180. Yeah, because the current's going negative. So instead of going like this, right? This is for positive current here. If I have negative current going in here, it actually goes in here. So now the magnetic field flip-flops, goes in the opposite direction. Okay?
And then also you heard the when you the sum of all the magnetic field, right?
Say it again.
There was a black line which is the sum of all.
Those are the sums. Yep. That's what we're going to get to next. That's what this equation is right here. So going back to what Stephen is, what are the X's and all that stuff? Those are directions. Those are vector directions. What's 1 at an angle of 0 equal to? Right?
Yeah.
What is 1 at an angle of 240 equal to? What's that? You don't need to use your calculator. Didn't everybody ever teach you? What's the sign of 0?
Yeah.
Sign of 30. Square root of 1 over 2, isn't it?
Yeah, 1 over 2, yeah.
What's the square root of 45?
Yeah, root 2 over 2.
You're getting it. What's the square root of 60?
Yeah.
Square root of 90. Notice that? Square root of 0, 1, 2, 3, 4, all the way. That's it. That's all you have to do. And the cosine is the opposite, right? So this is a square root of 4 over 2, square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, and the square root of 0 over 2, right? So that's how you can do it with the without using the calculator. Now you know the sines and cosines. The only thing that makes it difficult is 240 degrees is in quadrant 3. In quadrant 3, I have a minus sine and a minus cosine, right? And now what I need to do is I need to recognize that I'm rotating 60 degrees from there. So I take the sine of 60, which is a square root of 3 over 2. And the cosine of 60, which is a square root of 1 over 2, right? Cosine is the real part, sine is the imaginary part. So 1 at an angle of 240 is equal to 1/2 in the x direction, plus square root of 3 over 2 in the y direction. So let's just put the j term there, or y, either one. You can do that.
Supposed to be.
Minus, sorry, yep, they're both minus. So that's where these came from. Can you all figure out how to do 120? It's 30 degrees from here or 60 degrees from here. You take the cosine of 60, right? The sine of 60. And that's where you end up with here and here. You also have to recognize in quadrant 2, the sine is positive, but the cosine is negative. That's why we have, I think I have these backwards. Oh, no, this is a typo, sorry. No, this is okay. This is minus 0.5 plus, yes, that's correct. It's the minus 0.5 in the real direction. No, wait a minute. This is positive and this is negative. I've got those backwards. It's positive y and negative x, right?
Oh, yeah.
In quadrant 2, let me fix that real quick. This is plus. And this is minus. Okay. You can also do it if you don't like that, because this just shows you how to add the things vectorially. If you're not really comfortable with, if you're not comfortable with doing polar or rectangular, if you're not comfortable with polar coordinates, you have to do rectangular coordinates. This is just basically converting polar to rectangular. That's what that is, Steve.
And then also, instead of you add the minus 120 from the current, right?
Yeah, so this is the current. All this stuff right here, I still need to know where I am in time. So I'm just getting you the vector position. So if I'm at 1 at an angle of 240, that's just giving me the x and the y contributions this way. I still need to know how much current is in there. Is it 0.5? Is it minus 0.5? That's what these parts will give you. That's the actual equivalent to current. That's what that is.
But so now the formula is the V times current.
Well, I remember if I get a max current going through this winding, I'm going to get a max magnetic field. I'm assuming it's linear all the way through that current. I'm assuming the magnetic field follows the current. So if I'm at its maximum value, I get the maximum magnetic field. If I'm at 50%, I get 50% of the magnetic field, and on and on and on. So just to make it linear, to make it easier. I'm not going to worry about saturation because that would be too much. It's just, let's keep it simple.
And then also, why is the angle different? Like minus 120 plus 2.
This is the current angle for phase B. right?
Mhm.
So minus 120, isn't that equal to positive 240? And minus 240, isn't that equal to positive 120? Isn't that the same? If you don't like the minuses, you can change this to 240. And you can change that to 120. It's the same thing. So that's what you end up when you do all the math and adding things together. You have a bunch of X's and a bunch of Y's. And then when you sum them all together, what do you know? 1.5 B sub M in the X direction minus 1.5 B sub M in the Y direction. And you have that sine and the cosine, just to kind of simplify that. So we did this one already. So now we're going to add magnetic fields and we'll just do it by hand. So I've got some hand calculations. You can check this. So here is our machine, and I've got ABC exactly as shown. And I've shown you BA, BB, BC, and then I've got the BA here as shown. So now what I want to do, I want to run it at t equals 0 seconds. So what that means is time is at 0 seconds. So I can calculate the sine of omega t, the sine of omega t plus 120, and the sine of omega t minus 120. That's what I've got here. These were already determined based on where you were physically in the machine. So here's the actual calculation of those individually. So I'm doing these in polar coordinates. Now I add them up and I get 1.5 B sub M. Let's do it so that it's 30 degrees later. So I don't care what the time is because I can do this at any frequency, 50 hertz, 60 hertz, 40 hertz, it doesn't matter. Let's just make it so whatever the time is, that causes 30 degrees of equivalent rotation in your sine waves or your cosine waves. So these are all 30 degrees. Now the theta, so you can see 30 minus 90, 150. And here are my calculations. When I add those up, 1.5 B sub M at an angle of minus 60. Two things are happening there. The first thing is we're verifying that our magnetic field magnitude is always 1.5 B sub M. What's the other thing that I see here in my net magnetic field? The angle. If I rotated 30 degrees, I rotated from minus 90 to minus 60. So I was here, now I'm here. That magnetic field physically rotated, because this is in the real world, 30 degrees. So when I rotate 30 degrees electrically, I got 30 degrees of magnetic or mechanical rotation, which is if I have another magnet, I'm going to have that follow me. And that's how I get my rotation. This is in the counterclockwise direction, right? Rotates that way. Now, always the same. We love some MATLAB in this class, don't we? Look what I got for you. Happy birthday or belated Valentine's Day. Here are the exact values that we have. IA, sine of omega t, IB, sine of omega t plus 240, and IC equals sine of omega t plus 120. That's ABC rotation, is it not? Right? ABC, what we had, these are the same currents. The only thing I got rid of, if you look over here, is I got rid of the magnitude of I. I just let it equal 1, just to make it so that we have one less thing to do. And then my corresponding magnetic fields, these are the angles they're going to be at. Angle of 0, angle of 120, angle of minus 120. That should exactly match what we have here, right? 0, 120, minus 120. That's what we have here. So in MATLAB, I've got these values. Now, I'm going to go ahead and I'm going to clear everything, because remember, clear in CLC is nothing on my sleeves. It clears the workspace and it clears the screen. So there's no hanky-panky going on. I didn't build everything in MATLAB the way I wanted to. This just forces me to be honest, right? Nobody cares. Would you rather have me just, do magic tricks and then you just see how it works, or do you actually want to see legitimately with a calculator? I used to always, when I was a student, I used to drive me nuts when something would magically appear on the board and I had no idea if it was right. You're really like that too. You always check up, which is good because you're actually seeing how do I get there from here? This is how do you get there from here? This is just for Barzilai because he'll come back to me and he'll be like, there's no way you can get this. I'm like, Barzilai, no, you run that and he'll get the same thing. And then he'll be like, oh yeah, but he'll never say that to me if it's right. He only catches me if it's wrong. So here's omega t. I'm going to start at 0 degrees. I got to convert that through radians. Omega is in radians per second. Time is in seconds. So I need degrees. So I'm at 0 degrees. That's why I multiply by pi over 180 to get radians. Now I'm just running it through my currents. All I'm doing, running through my currents. Here are, and this is again, this is to Avery, which is how do you enter a complex number in polar? Remember that e to the j theta we talked about on Tuesday? This is e to the j theta. I'm building it with complex numbers. I have, and I don't include a multiplier for b sub m. I'm just saying let everything be 1. Whatever the current is, it's going to produce a unit 1 magnetic field that's going to be 1. That's its peak value. So these are whatever the current is at an angle of 0, 120 and minus 120. Notice I'm doing everything really specific. I'm showing you the degrees, but I'm actually, because MATLAB requires you to do everything in radian mode, I'm showing you the calculations. Now I'm going to do the total by just adding them together. They're complex numbers. MATLAB can add them together just like you can in your calculator. Oh, and by the way, I'm going to go ahead and display the results. I'm going to see what the magnitude of A, B, and actually not the magnitude, the actual current, because this is in the time domain. Then I'm going to look at the magnitude of BA and its angle, the magnitude of BB and its angle, and BC and its angle. And then I'm going to add those together and display what the magnitude of B total is and its angle. This is just displaying it. And then we go from there. So then this one over here is going to be at an angle of 30 degrees. So I'm just rotating 30 degrees. That's it. Here's 30 times pi over 180. Everything else in here is a copy. This is the only change that I'm going to do. Okay. So I'm going to put a hold here. And I'm going to run to this point. I'm going to make sure MATLAB is maximum size. You can see I was doing this already, but there's a bunch of stuff, but you watch. I'll even do it again, so nobody can argue with me. All right, so there's no variables. When I hit clear, you can't type any variable name. They're all empty. And if you don't buy that, open a variable. There are no variables in the workspace, so everything is clear, right? Even the screen will be clear. Now, Barzilai is going to catch me on this. I'm just teasing. I appreciate that you do that. Now I'm going to run it. And here are my results for angle of everything is 0. Okay. I have my currents. Let me just double check. Oh, it's right here. IA, IB, IC, IA, IB, IC. This is BA at an angle of 0. So 0 at an angle of 0, which is correct because there's no current. If IA is 0, shouldn't be any magnetic field. Here's B sub B, magnitude and angle, B sub C, magnitude and angle, and adding those together, I get 1.5 at an angle of -9. Which is what we calculated in the slides. So I just saved you an hour of checking those. Now I'm going to step through and I'm going to get all the way down to this display result. So step. Stop there. Okay. Now my current for phase A is no longer 0. It's half at an angle. I'm sorry, it's half. This is -1. And this is a half. This is BA, 0.5 at an angle of 0, B sub B, B sub C, and then total. Bunch of things being displayed here. First off, I can see that I'm getting that 1.5 magnitudes constant and I'm getting the rotation. The other thing is, look right here. These angles aren't changing, are they? 0, 0, -60, -60, -120, -120. because the magnetic field is always going to be, for VA, it's always going to be at 0 degrees, or it's always going to be at 180 degrees. It either goes this way or goes this way. It doesn't have any other place to go. The magnitude can change, but the angles can't. So you'll see all these angles not changing unless the current is going to go negative. So you can see these currents are always in the same direction, right? A minus and a minus, a plus and a plus. So those are going to be the same each case. What's interesting about these currents here? Why don't I have a magnitude and an angle for the current? Because I'm in the time domain. The time is 0 seconds. I is equal to a number. It doesn't have a magnitude and an angle. It's 2 amps, 0 amps. There's no magnitude and angle. The only time you get an angle is when it's over 1 complete sine wave. I'm doing this all in the time domain. The magnetic fields that I get from the angles I get from the magnetic fields are because I've physically got things going and I've manipulated them physically to get those results. Electrically, it's no physical, it's just, these are the currents. These are what the magnitudes are. So there's a lot happening here in terms of what's being displayed. And if you can understand that, it's a really setting you up for understanding 3-phase as well as magnetic fields, because we're jumping between everything is 2-dimensional going in this direction to now all of a sudden we can go everywhere. And I forgot to mention Steve comment, why isn't there a Z direction? Because I'm only in 2 dimensions, right? I'm not going in and out of the paper. Everything is going in 2 dimensions, an X and a Y, no Z. So last thing, this compass feature actually shows you the rotation. Starts off here, goes there. Now, the nice thing about MATLAB is I can change it. Let's say we want this to be 90 degrees. Now I'm going to clear all this, and it's going to, you'll see the screen clear and all the variables will clear. Now I got to wait for the compass to come up. And there you go. So we got 90 degrees equivalent of time domain rotation. Gave me 90 degrees of physical rotation. And the magnitude is exactly the same. You'll also notice here too, remember how I said some of the angles, they're going to be the same? Well, let's see. This is my current for phase, my magnitude for phase A, no angle shift. This is the magnetic field for phase B, no angle shift. Hey, what do you know? A shift between C, right? For the first case, that's because the current you can see was 0.866. Now it's negative 0.5. So it now goes in the opposite winding. So what is the difference in degrees between minus 120 and 60? 180 degrees, exactly what we expect. I was hoping to be everybody be more impressed. Seems more like you're just like, huh? What? You're the only one who was interested in it, so I'll just post it for you. I'll give it to you. Unless anybody else wants it.
Yeah,
Yeah, I'm kidding. I'll make it available. I'll post it to the class. But this does a lot of things, but it's all the calculations that we did. Literally, you could stop right here. You have 5 or 6 lines to do all the calculations we've done. I just made it so that you can hopefully understand it a little bit and you can kind of walk your way through. So I did 90. You can do any angle you want. Want to do 180? Let's see the compass. Exactly what we expect. I don't know why it reset it, but this is still 1.5 because this right here is 0.67. This is 1.33. It's still 1.5, right? You can see it's slightly over, but for some reason, I don't know if MATLAB gets confused because you're adding complex numbers, but it's still 1.5 rotated 180 degrees. Questions on that? Is this helpful or confusing? Or both?
So it's kind of digesting.
Yeah, digest.
Well, it's not a lot of new material. We're actually really pushing you because now what are we doing? We're very comfortable living in the electrical world. Everything flows to that wire. It's easy peasy. We live in all these different dimensions. So I've just challenged you by saying this current over here is getting a bunch of vectors over here. And in EET, we don't cover a lot of vector math. The ECs probably think, oh yeah, this is easy peasy, right? Maybe not, but I'm kidding. Yeah, you do vector, but it's hard to understand because now you're trying to envision things that are outside the electrical realm. And we need that to be because we can't just run electricity into a wire and not understand how you get these vectors and get this rotation. That's critically essential to us. But this is how the basis of how you form magnetic fields in AC machines. And in whether it's a synchronous machine or induction machine, we'll learn about the differences in a little bit. You'll actually see that the stator is exactly the same. There's no difference. You have to get this rotating magnetic field. But yes, I'll post it to today's class. And that way everybody will access it. This is just for your own, I try to put this up there because people, like I said, Barzilli is really good at correcting me if I make a mistake on the slide. In reality, what happens is that he likes to check and do this stuff because that's how it helps him understand. So I thought I would put this together because there's a lot happening here and it can be a lot of confusion. So now Barzilli can say, well, I don't maybe like MATLAB, but I'll run through my calculator and see if I get the same results. And now, no way he's going to say I got it wrong. I'm going to say, go argue with MATLAB. They wrote the code. I just kind of follow. But yeah, I'll put that up there so you all can check it out. You're not required to do this in MATLAB. This is just, an additional, hopefully helping you understand it. Because looking at the slides, I could see everybody's like, what? How take my glasses off? What's going on here? It's hard to envision. It's very difficult to envision because now we're stepping outside the electrical world, which is very simple in terms of, what's happening. Now we're in 3D. Which is interesting because if you ask most engineers, they'd rather do mechanical because they understand it better. They think they do. Touch it, feel it, whatever. But I happen to be, when we gave out our test on Monday, somebody had notes from an EET321 class. And that's all you saw was X hat, Y hat, and Z hat, all these vectors to be able to do it. And we can no longer stay exclusively in our electrical world where everything stays in that wire. Because it doesn't do us much good. Right? The mechanical world is three-dimensional, so we need to be able to understand. But I will put this up there for anybody. Questions on any of this material? Yes, sir.
Understanding.
I mean, you could watch the video again. Obviously, that'll help. Maybe you can understand some of the vector stuff. If you can go through MATLAB and see the calculations, and this is where it gets hard because if you don't understand the syntax in MATLAB, it can be a little bit challenging. But if you can go through and understand the syntax, you can start to see, hey, where did he get this from? How did he get that? And then you might be able to track it through into the physical locations of things. That might be the way to do it. But it's hard material to grasp. In some ways, this is the hardest material this semester, is being able to understand the vectors. But we really need to get into vectors to understand machines.
How is the regenerative?
The regenerative? Excellent question. So we haven't gotten to there yet, but the way you get regenerative is you have a magnetic field, you have something that's rotated this way, right? And you basically are trying to introduce voltages that would give corresponding currents that would rotate a vector in the opposite direction. So what ends up happening is instead of pulling it along, it's slowing it down. So these currents here, we'll actually learn how you can create those currents just by basically slowing things down. That's all it is. So regenerative means either, if you really want super fast braking, make it go in the opposite direction. But slowing it down means this is what the magnetic field would be on that rotating part. The one that I want on the stationary part is going to be here. So this one is dragging, this one drags this one. This one's slowing it down, so that's how you start to get rid of the energy. That's regenerative braking. Anything else? Feel good? Bad? Tired? It's okay. I'll put this video up, and like I said, I'll have the MATLAB script. And if you want to play with the MATLAB script, this is a good challenge for you. Over the weekend, swap A and B and see what happens. Instead of the current going into that top, that winding that is top and bottom, swap it so that it's running into B. Which means B now has to be swapped to A. Make sure you maintain a 120-degree phase relationship, like we talked about. See what you get. Any questions in TV land? Thoroughly confused? Okay, it hurts. Your head hurts because it's vectors. But you'll get there. If you just keep working at it, you'll get there. So. All right, if there's nothing else, have a wonderful day and wonderful weekend. I'll see you all on Monday for lab. Take care, everyone.
Thanks, Paul.
Yep, see you guys. Bye.
Paul, quick question, actually.
Yes.
You say